The first topic is about some safety considerations, emergency consideration in the process. Usually we have in the process, most of the time we have vessels that we call it also pressure vessels. That these pressure vessels they contain either liquid or like compressed liquid or liquid at high pressure or even gas at high pressure. And also there are many vessels like distillation column, reactors, pumps, compressors, storage vessels, storage tanks. They are not operating at atmospheric pressure. Most of the time they are above atmospheric pressure, and sometimes due to some issues there might be some excess pressure or some like unexpected increase in the pressure that we have to predict it, and we have to take some necessary action about that. So in what are those cases that we can have some overpressure or high pressure in the process? If there might be some operation problem, let's say human error, or one of the equipment they fail, or like the equipment, one of the instruments, let's say the instrument that adjust the pressure or adjust the flow rate, the valve, the pressure meter, there might fail. There might be a process upset. Let's say in reactor we have a uncontrolled reaction. The temperature will increase and at the same time pressure will also increase. So this is called the process upset. So this can also increase the pressure in the reactor. Or external event or fire. Let's say there is a fire somewhere in the process, or there is a stormy weather that it will destroy or damage one piece of equipment, and then that equipment catch fire. So those are utility failures. Let's say one valve fails, one pressure meter fails, one level meter level. So those are the cases that we might have some overpressure or higher pressure than what is expected in the process or in the equipment, that we have to find a way and relieve this pressure. That we usually use relief devices, relief valves, like there are valves like what you see here. I think I believe in PO 1150 you should have seen this type of the valve, because one of the topics that we will cover in PO 1150 is relief devices or relief valves. So it's such a valve that I'm gonna explain a little bit about this type of in general relief device or relief valves. So okay, in which case we need a relief event. Relief event means relieving the pressure. We need to just discharge or purge the pressure from the system. As I said, external fire. If we have a flow from high pressure source, let's say we have a high pressure tank or a column that is working at high pressure, there might be some heat input to a piece of equipment. Let's say you have a tank, you have a storage tank. For any reason there will be an increase in the temperature of that tank, or there will be one heat input to that. Let's say the heater of that tank or the cooling system of that tank fail, so the heat will be added, or there will be increase in temperature. That usually increasing in temperature also increase the pressure, because increasing temperature can vaporize the liquid and make more vapor, increase the pressure, or for the gas we know that PV is nRT. If temperature is increased, pressure will also increase. Pumps and compressor, those are equipments that they use. Pumps that increase the pressure of liquid, compressor increases the pressure of gas. So those are the equipment that we have change of pressure, so we have to control them accurately. Ambient heat transfer, so let's say in the summer days, especially here, that temperature goes up, so the equipments they catch more heat than like winter time, or let's say at night. So those are the cases that we might have some increase in pressure and we have to relieve it. Liquid expansion in the pipes or surge tank also is cases that we can have is also cases that we can have increase in the pressure. Then code requirements. Okay, so this relief devices or relief valves in general, they have kind of design requirements. Okay, so we have to consider what will be the possible scenario that we need this kind of valve, what are the possible scenarios that we might have some excess pressure in the system, and how much will be, in worst case, how much will be that excess pressure that we have to relieve it, right? So based on all this information that we have to go choose and pick the right relief valve. Okay, and there is in some of the slides I will explain, if you don't pick the right equipment, what will happen to the process or to the device itself. So first of all the pressure vessels, whatever pressure vessels or pressure tank that we have, we know that the pressure is high and pressure will also increase. We need to design such a relief valves. Okay, in all equipment, in all piece of equipment that we have high pressure, let's say pressure vessels, pressure tanks that I already that we already know like which type of tanks they are, we need to have a relief valve, okay, to protect this vessels, these devices. If we have a vessel which is, or a pipe system, piping that is filled with liquid, and we know that liquid, it might goes to a thermal expansion. Thermal expansion means that there might be a change in the temperature, increase in the temperature, okay? There might be an increase in the temperature, that this increase in temperature can lead to increase to, okay, it's a thermal expansion. So there might be some cases that there will be an increase in temperature. This increase in temperature can also increase the volume, okay? Thermal expansion for liquid means increase in temperature that leads to increase of volume, that if it's in the limited space, the pressure in that space can also increase. So in that case, to protect the device, we need also a relieving system like that. Multiple vessels, okay, so when we have multiple vessels, or let's say connected tanks, connected vessel, connected pressure vessels, when we have multiple of them, we can use one single relief device. We don't need to use several, okay, but as long as that we are sure that there is no obstacle, or there is no there is no issue between in the network of this vessel. There is like all these vessels are connected properly, and if let's say there is one increase in pressure in one vessel, that can be detected in the neighboring or in the other vessels. Then for sure we need to all the time, okay, when we have pressure reliefs, okay, pressure relief device, such devices, you know, like each of these devices, they have a set point or set pressure, that, you know, they have such a springs here that we can choose the type of this spring, or there is usually a screw here that you can turn this screw and you can change the tension of this spring, and by changing the tension of that spring you can change the pressure that the valve will act, okay, the relief pressure, in which pressure the valve has to be open or closed. You can change it. So there is also okay, so we have to, and also all the devices that we have, any equipment in the process, it has a parameter that is called MAWP, maximum allowable working pressure, which is the maximum pressure that is allowed to reach in that equipment. If we pass this MAWP, we can damage the equipment, okay, we can damage the equipment, or in some cases we might have explosion, or we might have, you know, the equipment might burst. So we always set the relief device, okay, we always set the relief device below below this. Most of the time we adjust, we set the relief valve below this maximum allowable pressure. By the way, the maximum allowable working pressure, okay, is far from the pressure that that equipment might burst or explode, okay. This pressure, maximum allowable working or operating pressure, is usually far from the pressure that will lead to explosion, or like to the burst of the equipment. And the reason is that like this is for safety. Like we define this pressure for the user, for the operator, to make sure that he's all the time working under, or very close under, or in the worst case close to this pressure, and he doesn't pass it. If he passes, that is a like he has to receive a warning that he's past the MAWP, the maximum allowable working pressure. And we usually set this valves in this pressure or below it, okay. So if the pressure in the vessel reach to this pressure, the valve will be open. Then in general, as I said, okay, to make sure that the relief valve is not going to be open, unnecessarily. To make sure that the valve, it doesn't open or it doesn't take an action that is not really critical case. So as I said, it's better to have all the pressure valves, relief valves, to work at this point or below it. But in some cases we can set the relief valve, the relief pressure, the pressure that the valve relief or will be open, a little bit above this pressure as well, okay. Because as I said, the maximum operating pressure is not really the pressure that we might have explosion. So we can adjust the relief pressure, the relief valve, at a pressure a little bit above this, to make sure that the valve, it doesn't open unnecessarily. So there are some, it's common that in the process the vessel goes a little bit above the allowable working pressure, but it's not still dangerous. We don't want that as soon as the equipment reach to this pressure, the valve start opening. We can give it a little bit more room. So for example, there are some cases here. For example, for the fired or unfired steam boiler, we can set the relieving pressure like 3% more than the MAWP, a little bit, 3% more than the allowable pressure. If let's say we have vessels, like multiple vessels, that has only one single pressure relief device, so we are allowed to set the pressure up to 10% more than this pressure. If we have, let's say, multiple vessels that they have also multiple pressure relief device, so in this case, since we have multiple pressure relief device, we have more freedom, so we can set the relief pressure up to 16% more than the allowable pressure. And in case if there is in case there are some possibility for the fire, okay, that in the device, in the process, in the equipment, we can adjust the relief valve up to 20% more than the maximum allowable working pressure. But this is kind of general rule. It can change from one equipment to another, from one process to another. Then okay, so How we design such a device, how we design such a valve, relief valve. So first of all, we have okay, where we put them, all the vessels, pressure vessels, or even vessels that are working a little bit above the atmospheric pressure, we need to have such a valves. In the discharge of compressors or compression equipment, okay, discharge of compressor are usually in a storage tank that has high pressure, so we should put such a device in the discharge of the compressors. And we have, depending to the application, we can use relief valves, pressure relief valves like such as this valve, or we can have also rupture devices. Rupture devices is a very simple device. It's like a metal disc, like this disc here, that it's usually okay, that is installed on the vessel, on the pipe, that block the vessel, block the pipe. So once the pressure in one side of this rupture disc goes up more than the pressure that is allowed in this rupture disc, so the rupture disc will burst or rupture, and it will relieve the pressure in that way. It's usually used for liquid surface with a very viscous liquid. Okay, so like we can use this device or this one. How? Okay, then we have to develop scenarios. We have to sit and think about what are the worst cases that can happen. What will be the worst case scenario that we will have pressure in that equipment? What will be the maximum pressure, maximum flow rate that we need to relieve in that equipment? Then we will use we will size the relief. We will use some calculation and find the right size of the relief valve, as I said, choosing the worst case scenario. And also at the end we will design the relief system. If we need one relief valve, if we need multiple relief valve, this is what we will design at the end. Okay, so as I said, we can use a spring operated valve or relief valves or rupture devices. Okay, so relief valves, they usually have a spring that's why we call them a spring operated. So here you can see in this animation that I put for you, at first that the pressure in the line is not a lot, so this valve is closed. Okay, once the pressure in this line increase, so the fluid, the liquid here or the gas will push this spring up, and the gate will be open, and it will relieve the pressure, and the pressure will increase. So as I said, there is a stem here, there is a wheel here that we can adjust the tension of this spring, and adjusting the tension, it means adjusting the pressure here in this part. So I mean the relieving pressure. So like in which condition we will use it. So when first of all, when in the case we don't want to lose the total content, the entire content of the pipeline or the vessel, we don't want to lose, we just want to lose a little bit to adjust the pressure, that's all. When we have fluids that are operating at above their boiling point, when we have toxic liquids that if we relieve all of them, if we lose all of them, so it can be dangerous for the workers, for the environment, society, whatever. And then we want to go back to the normal operation quickly, so here the valve will be open only once it is needed, and once the pressure is relieved, it comes back to its initial condition and the process will be working normally. Okay, so we want a quick action, quick return to the normal operation quickly. And this valves can also tolerate the change in the change in the process pressure. So as I said, we have such a stem here that we can move it clockwise or counterclockwise, and by moving that stem we can adjust the relief pressure. So let's say if that pipeline tomorrow or next week is working in different pressure, so we can also adjust the relieving pressure here. So it gives us a lot of flexibility. Rupture disc that you can see here, so once the pressure in the is used in the pipeline to block the pipeline or vessel, and once the pressure increase up to a certain pressure, which is the rupture pressure, so the disc will rupt, the rupture will happen, and it will relieve the pressure. So in which case we will use this type of device first when losing all the contents is not an issue, is acceptable, because like when the rupture happen, it cannot comes back to its initial condition that was blocked or closed. Okay, so in that case we might lose all the content or the big amount of material. So if for us there is no issue to lose, is fine. Then since usually we relieve a big amount of materials, so we have to make sure that we install it in a pipeline or the vessel that doesn't have toxic or dangerous material. So for safe service or non-toxic or non-hazardous material or streams, it will be used. It's a very fast acting device. It will act quickly as soon as pressure reach to a rupture pressure, it will rupt. And in case if we have plugging, in case if we might have plugging in the relief valve, in the pressure relief valve, we will use this kind of device. So pressure relief valve has an opening. Pressure relief valve has an opening. If this opening is blocked, or with some solid particles or corrosion or for whatever, and like that will affect the operation of this valve, so we prefer to use such a devices. And for high viscosity liquids, these valves are also more preferred. Then okay, there are some equations. So what we have to do for the relief orifice area, here, this area here, for the relief orifice, the area here, so we need to do some calculation. Okay, when we are talking about sizing the relief system or relief valve, one of the main important parameter is this area, the area of that orifice or the relieving areas, that depends to the capacity, the maximum capacity of the air or the gas or liquid that is going to go through that orifice, and also some other parameters like pressure, temperature, density, and some other operating parameters. There are few equations that can be used to calculate that area that I'm gonna just show them to you. So first of all, for each system, either liquid, gas, or vapors or steam, we have different equations. For liquid service, this is the equation that is being used by most of the engineers. A is the area, Q is the volumetric flow rate, G is the gravity, Kp, Kw, Kv, those are all some factors, some correction factors that will be given to you and is available in the handbooks, in many valve manuals, handbooks. And differential pressure, which is the pressure like before and after, the set pressure of the valve and back pressure. Okay, so if the valve is connected to the vessel, so is the pressure that is set here. Okay, the set pressure, the set pressure and the pressure here. Delta P is the difference between the set pressure of the valve and atmospheric pressure. Not atmospheric, because this vessel, it might be connected to another vessel. So the pressure is not necessarily atmospheric. The exit of the pressure relief valve might be connected to another equipment or to another place that doesn't have necessarily atmospheric pressure. This is for liquid service. For gas services, vapors or gas services like not vapor, I mean like all the vapor except the water vapor or steam, we will have such an equation that again we have W, which is the gas flow rate, T temperature, Z compressibility factor, C K. Those are some factors that will be given to you, is available on the okay, even KB. Those are some factors that you need to use. M is molecular weight. P is also the upstream pressure, the pressure before the valve. I mean the pressure, if the valve is connected to a vessel, the pressure of this vessel. And I mean it can be set pressure plus overpressure and atmospheric pressure as well. Then okay, for the steam systems, steam services, we will use this equation. Again, W is the flow rate, PI is the pressure, K, Kn, Kc, Kch, Ksh. Those are some factors that will be given to you most of the time. And yeah, as you see, like most of them, they are very simple equations. You just need few parameters you can put there and find the diameter of the orifice or the relieving section. Okay, chattering. So like I put one YouTube video for you here, please watch it. This presentation is also available on D2L, so you can download it and copy this link on your browser, so you don't need to type it all here, like as you can see here, because sometimes it's difficult. So chattering is an issue in relief devices, is chattering, or we can call it singing. Okay, when the valve starts singing, and you see this this figure here, it shows what will happen to the valve. So chattering is when we choose a wrong valve for that process or for that vessel or that equipment. When we choose a valve that is not fit to that pressure, to that flow rate, and to that equipment. So it's when the valve will be open and close rapidly. There will be a continuous opening and closing of the valve that will make a noise, like a chattering noise. And since the valve will be open and close rapidly, okay, will be open and close rapidly, it can damage, you know, like it can lead to misalignment. It's like it can create a big vibration. It can damage the seat, the valve seat, and if it continues, it will be associated with some mechanical failures of internals of the valve and even the piping system. Okay, so is an issue in the relieving system. So this exercise is important. Please try to learn it in details. And usually, okay. Okay, usually, let's say if you once you are sizing the valve, you will find the maximum you will find the maximum capacity of the valve. You calculate the valve based on the maximum capacity, which is, let's say, the flow rate of 100 kilogram per, let's say, 100 kilogram per hour. Just imagine like this. So usually we need 25. So you design your valve based on this maximum capacity. Your valve has to be able to allow this much fluid if it's open, 100 kilogram, maximum this much, 100 kilogram per hour. So usually 25 to 30% of this maximum velocity or maximum capacity is needed to keep the valve open. Otherwise, the valve will be, chattering. Okay, lower flows or lower flow rates, lower velocity will lead to chattering. That is the issue, and it can damage the valve. You can watch this video; it will show it, I think, the better way. Okay, so chattering can be due to two reasons: valve issue, the design issue, and also the relief system issue. Okay, so like where it is installed is wrong, it's installed in the wrong place. So valve issue, as I said, it can be an oversized valve. Like we are using the valve, we are using a bigger size than what is needed. And valve is handling a really different flow rate or different fluid. Okay, so this can be the reason, or the pressure here. Okay, excessive inlet pressure drop. So if the valve, again, if it's choose in the wrong way, is handling a liquid or fluid or vapor that is not designed for, so there might be a big pressure drop in the inlet of the valve. Okay, in the inlet and outlet of the valve, or that will lead to chattering, or if there is a big back pressure, if there is a excess back pressure in the relief section of the relief valve somewhere here. So those are also cases that we might have chattering, so we have to avoid it. Then okay, that was about relieving system, which is which is really related to the safety of the process. Now I'm going to talk a little bit about environmental impact of the process. So any process that we design and we are going to install, we are going to run it, should be environmentally acceptable. It should be based on environmental standards, environmental regulation rules. That first of all, these rules, this environmental standards are required by law. So I remember that in Qatar, when you are going to do tenting, when you want to have a tent somewhere in the desert, like let's say anywhere in Qatar, that usually people they do it during the winter or during the fall. So as I remember that some of the students they told me you need to have a permission from environmental ministry, environmental office, right? So even for doing small things like that, you need a permission to make sure that you are not damaging the environment. And imagine for a plant that is producing a lot of waste, a lot of emissions. So this permission, this kind of regulation is even more restrictive. So the environmental standards are required by law. There are laws about that. Okay, sometimes if we break this environmental standards or the laws, we can have a catastrophic effect on the human, social, and economic, human life and society and economy. There are many examples of like catastrophic events or accidents that happen around the world, and with a huge impacts on the bad impacts actually on the environment. And there are many cases, many examples. One of them is Chernobyl. It's the atomic reactor in Chernobyl that which is like the biggest catastrophe in our century, and we have not yet got any other any bigger accident after that catastrophic issue with the atomic reactor. Then Okay, so then if we don't respect the environmental standards or the safety standards, what will happen? So the insurance, they get more expensive. The stock market, the stock prices will also increase. That will affect the economy and the life of the people. And also, this is also something related to the moral and ethical things. Is a moral and ethical obligations. We all feel some responsibility for our future generations, so we have to respect our environment. We have to respect the environment. We shouldn't damage it, because this environment is also this should be used by the next generation, right? So those are the important points about the environmental impacts of the process and some considerations. Okay, there are environmental regulations either globally or locally for each country. So like each country has his own rules. Qatar, Canada, they have, or other countries around the world, they have their own regulations. Some of them are really tough and very restrictive and very sensitive, and some of them are also, like they are not that restrictive. For example, I know in Canada, they're very it's very restrictive, and you have to follow a lot of laws and rules to be able to do some kind of production activities. Okay, and most of the time, okay, so the governments, they will regulate this things. And for example, in a chemical plant, in the chemical engineering, which is our field, so the governments, they are asking you to continuously monitor, document all the waste streams that you have and is discharged to the environment, the contaminations, the amount of the waste, what is included in your waste. Those have to be documented, monitored continuously, and systematically. Then maintain the necessary permit. Okay, so you have, for any activity that you do, you have to have the relevant governmental the permits from the relevant government agency. And in case if you if you involve in any violation in the process in your plant, you have to pay the corresponding penalties and fine. That is usually huge amount of money that most of the companies, they avoid to get to any violation, to get involved in any violation, to avoid paying such a big penalties. Okay, in general, the government agencies, like let's say environmental ministries, they have that much power that they can seize operation. They can stop operation of the plant and even send the management to the jail. Okay, so in the extreme case, this can also happen. Okay, most of the time when we are designing a plant, we will talk about environmentally conscious design or environmentally smart design. That is a design that we consider all the environmental consequence or impacts of our chemical process and product. So like like some of the terms that is taken into account in environmentally conscious design is we have to quantify multiple environmental impact. We have to do a lot of accurate calculation to know what is our quantitatively what will be the environmental impact, how much CO2 we are releasing, how much waste we are releasing. Okay, we have to do really accurate calculation for that. And okay, so when we design the process, and the product, so that in general those two activities, we also consider environmental impact. If like recycling the streams, reusing the streams, producing some byproducts, then wasting. So those are the things that will be considered And also we have to always try to improve the environmental performance of our plant or chemical plant and product. Those are the things that we consider in environmentally conscious design. So again, we have to, like consider the environmental impact and economic performance. I mean, how much energy we consume, what will be the impact of our process to the air or water, what will be the impact of our process to human health, what's the cost of our process and how much profitable it is, profitability, how much raw material we are going to consume, how much solid waste, liquid waste we are going to produce, and finally how much toxic material we are going to produce and how they will affect the ecosystem. Those are the important points that we need to consider. Okay, so there is a waste minimization hierarchy that this is one example that has been designed by like a city council, Burnley City Council, but we have this type of hierarchy for different process, different application. Hierarchy is like it's kind of shows off what are the steps that we have to follow and what is the importance of that process, of those steps. Okay, this is the general steps: avoid, reuse, recycle, waste to energy, disposal of the waste. So the first thing, important thing that we need to do is to avoid consuming, right? We have to reduce our consumption, and it means maximum conservation of resources. We have to conserve our resources, we have to save our resources, if to just use it when we really need them. So we have to reduce our consumption, even eating, wasting food, like those are points that we can do it personally that will affect the whole universe. Reuse, okay, so there are many materials that we can reuse them, right? So there are cars that we can use them for many years. There are devices, let's say laptops, many products, cell phones, we can use them for many years. Or if let's say we don't need them today, we don't need to waste them. We can just keep them, maybe tomorrow, day after, we can reuse them. Recycle, if we really need to waste something, so it's better to recycle it. If we really don't need laptop, nowadays there are there are companies that they recycle electronic devices. They recycle cell phones, laptops. Why? Because each laptop, each electronic device, it contains plastic materials. It contain let's say different type of metals like copper. Very expensive metals actually. So those companies, they receive this waste, let's say electronics, and they will separate different parts and they recycle them. They recycle and reuse the copper, recycle the polymers, plastic materials, and almost big parts of the electronic will be recycled. Waste to energy, if you really have to waste something, instead of sending it like that to the environment, just living in the environment, most of the time you can convert it to energy. Like waste to energy is a big industry these days, that let's say we can produce some chemicals, value added chemicals, or even energy by using the waste. And at the end, the last step is really disposal to the environment. If we really cannot do anything about that thing, that waste, if we cannot reuse it, recycle it, or convert it to energy, we will dispose of it. So this is one example. There are many other examples in the internet. You can just search it. Then okay, there is another chart, like those are the charts that is usually used by the designers when they are going to design a process or equipment. They use such a chart, such a graph, then they will see where they can, in which of this like which of these cells or these items can be applied in their design. Recycling, waste to energy, like you reusing. Those are the things that they will see what are the potential of that process or that equipment to apply each of these items. So in general, waste minimization technologies contain the three major work: recycling, source reduction, okay, using less raw material or less resources. Recycling is a very important step, by the way. Then product modification, modifying our product to be used for a longer time or do the same job with a higher performance, with a higher with a better quality. Then okay, recycling, it can be on-site recovery and reuse. We can, let's say, use separators, separate some chemicals, send it back to the reactor and reuse them and recycle them. Or if you are producing some waste, we can clean the waste, we can treat the waste and reuse it in the system. Or let's say producing some byproducts, okay, before wasting that component, that chemicals, we can convert them to some byproducts. This is happening in many processes. Source reduction, to reduce the consumption of the resources or raw material. What we can do, we can change our process, modify our process, good housekeeping, or maintenance. This also help us to reduce the use of our raw materials. Then okay, process change, again, it can be changing the input material. Okay, we can change the material, we can make them more pure by using some separation process, or even we use the material that is best fit to our process. Better process control, if we can control the processes more accurately, more precisely, so this will also lead to a better quality, product quality, less waste, less pollution emission. Equipment modification, we can change the design of the equipment, and this will be also connected to the better control and process control. And technology change, sometimes we can also change the technology. Let's say for treating the waste, sometimes we can use fermentation, we can use combustion, we can use gasification. Those are the process technologies available. So that's kind of gives you some idea about how to minimize the waste. So maintenance is a very important activity in the process. If we do a right maintenance, a good maintenance, we can save a lot of money. We can produce a very good, higher, better quality products that is in the benefit, and we can avoid producing waste. Maintenance, there have been a big development in the process maintenance, let's say since 50 years, 70 years ago up to now. Okay, 60, 70 years ago up to now. So, like they are saying that in general there are three generation of maintenance works. Okay, so the maintenance activity, which is also a process, which is also a, like each company, they have a group, they have a team that is a maintenance team. Okay, and they have a really, they have a very good protocol to follow and to do the maintenance activity. But like many years ago, when the industrial revolution just started, so the maintenance was not very, was not taking very seriously. But okay, okay, so there have been a lot of development. So before, like those early years that we had kind of industrial revolution, most of the plants, they just started producing products. So it was the maintenance was just fix it when it's broken. Okay, they were waiting to see if something is broken, it's not working, they were fixing it. Many years after, 20 for 30 years after, it becomes more detailed. Okay, so they wanted to have higher plant availability. They wanted to plan to work, I mean, more continuously. They didn't want to stop a process, and they wanted to have to use the equipment for a longer time. They wanted to have a longer life for the equipment, and they wanted to pay less cost. So they prepare the maintenance activities based on these objectives. And after that, I mean, the recent years, in the last 20-30 years, so the maintenance has been much more accurate, and it's been like a bigger activity that is aimed to reach to a higher plant availability, better safety, better product quality, no damage to environment, longer equipment life, and also the less cost or more profit. Okay, so those are the things that is being considered that is being considered when I mean, for the maintenance activity in the recent year. And okay, so the techniques, the technology that was used, okay, that has been used for this job has also changed. We had, okay, so before it was just fix it when, in the first generation, fix it when it's broken. In the second generation, you know, they were some systematical and scheduled overhaul. Overhaul means, you know, like, let's say they were stopping the heat exchanger after each few months, and they were cleaning, fixing it, and then putting it back in the operation. So that was a scheduled overhaul. System for planning and controlling work. So like they had a work, you know, like a systematic workflow, planning work, and, you know, like for maintenance. And also like computers, that was those times that they were big and slow, they also help for this maintenancing, you know, the scheduling the maintenance. But third generation, okay, so like in the third generation, we had more technology, more instrument that we could monitor the condition of the equipment. There were many technologies, softwares that you could design, you know, and the maintenance works. And there have been many hazard studies, and these days we have very fast and small computers that can be used. And there are many, you know, analysis like for failure mode and effects, you know, like a lot of simulation about that, a lot of expert systems, you know, there are a lot of people that are expert in this job that this day they have been educated in different, you know, institutes. And also multi-skilling and teamwork, you know, like teamwork is also encouraged, because maintenance is something that most of the workers, they have to be involved and collaborative to do it carefully. Okay, so the new development or the new development or the new methods or technologies for maintenance is aimed for total productive maintenance, TPM, or total productive maintenance. So that is considered to use tools for hazard studies, for the failure and effect mood and the failure mood analysis, okay, applying the expert systems. Condition monitoring is also new technology or new methods that you can monitor the condition of your equipment. If it's in a good condition, bad condition, if it's working its maximum capacity, or there is some issues, so you can really monitor. You don't have to wait until the equipment fail and then take some action. You can really monitor the condition of that equipment. Nowadays we have more technologies for fabrication, for construction, so we can design and build equipment with a better accuracy, with a more emphasis on reliability and maintainability. Okay, so that's another thing that for the design equipment. And also there has been a major shift from individual working or thinking to organizational thinking. Okay, organizational thinking by you know, like encouraging the participation, team working, and being flexible. That is, all of these activities is aimed to lead to a total productive maintenance, or TPM. Okay, so about also designing so designing the plant is also, you know, when we are designing the plant, the designing equipment, there is one phrase that is saying that designing plant for safety. You know, it's very important that even if in the plant there are some equipment that they fail, or if there is a maintenance work is going on, so the plant is still safe. Okay, so you might hear this term fail safe. Okay, fail safe mechanism is that the equipment, it has been designed in the way that even if it's failed, the process will be still safe, the equipment will be still safe. That, as I said, one of the examples how we can make sure a fail safe mechanism, let's say designing some switch, emergency valve, some pressure relief system, this kind of system, they all help us to reach to such a mechanism. Then during the maintenance, okay, when there is a shutdown for maintenance, we have to also make sure that the process is safe to do the maintenance. Let's say sometimes you have equipment that you need to clean it, so you will commission that to outside. You will bring a contractor from outside, like a company that is expert in cleaning, to clean that equipment. So you have to make sure that the process is safe for them to come and do the cleaning. The maintenance work is also being done safely. Okay, so like there are many cases of you know, like really catastrophic accidents, that let's say they stop one equipment and they start doing the maintenance. They didn't think really what will be the effect of that stopping that equipment or that maintenance to the other part of the plant, that led to really, you know, like explosion, or, you know, to a very bad accident. There are many cases, you know. If you just search in internet, YouTube, you might find, you know, those cases. You know, like in aviation industry, you know, for the maintenance is a very important part. And whenever the maintenance is done on the aircraft, usually when they land, there is a protocol to maintain to check many things in the aircraft. So like once they do the maintenance, the overhaul, they have to submit a very accurate, precise report to the managers or to the pilots, so to make sure that the aircraft is safe to take off, or, you know, to work again. So those are some points that we need to consider. Okay, so when it comes to the maintainability, I mean, like one question is always what's the optimum age of equipment or a part to be used in the process. Okay, to do that, to find the optimum age of a part, okay, equipment in the process, there is always such a curve, like that can be used by the designer, by the managers to make some decisions. What is this curve? So you have in the y-axis you have cost, in the x-axis you have MTTF of the part of equipment. What is MTTF? Is mean time to fail. So it can be, let's say, days. Usually it's days. It can be days, it can be weeks, it can be years. So you have mean time to fail is the time that equipment, that part will fail. So for that part, the capital cost usually at early age, early days, early years is not increasing, because let's say inflation is constant, so you buy that part, that equipment, you will install it, so you don't pay really any money until that part start to, you know, let's say if it's a compressor, so you need to repair the compressor continuously, you need to change the parts, you need to do a lot of you need to change the parts of that compressor, sometimes you need to change the motor, the driver, the shaft, so that increase your that increase your cost of that equipment. Once it's, you know, you start using it, after a few months, few years, it start to become costly for you. It's like a machine, like a car that gets old, it has more money to change, you know, you have to change different parts, you have to change the you have to change you know, the tire, this kind of thing. That is usually capital. Maintenance, so the equipments, you know, once they are installed at the beginning, they need a good maintenance, you know, like, because you need to fix a lot of things, you need to, you know, like change the oil, let's say, continuously, you need to make there is no leakage continuously. So at the beginning it has some kind of maintenance cost, and but as long as it you know, like it start working, the maintenance cost will be less, but capital cost might increase. There is a point, there is a age, there is a range that this total cost, which is the maintenance and capital cost, will be minimized. Like let's say this range, that is the minimum total cost. So is this range tell us the best is the range that we can use that equipment or that part in the best way. Is the best time of range of time that equipment or that part can be used. Out of this one, you can see that the total cost will be more. So we have usually such a curve, such a graph, such a tools to be used for maintenance job and evaluating the maintenance and the cost of the equipment. Okay, designing the plan for the maintainability. So when we are designing a plan, there is kind of 4 design requirements for the maintainability. For the maintainability, there is 4 requirements. First, easy to access. Each equipment should be easily accessible. We should be able to have access to them easily, to repair them, to change them, to replace them. A standardization of equipment, so all the equipment, they have to be working in the standard condition, the standard design condition. We have to evaluate what is the skill level that is needed to maintain that equipment. Okay, this also we need to evaluate this, we need to report this. And also redundancy of running equipment. Okay, so we have to evaluate like after how many months or after how many years we expect to repair or replace that equipment. Okay, so those are the 4 important things that we have to consider when we are designing the equipment. Okay, one example, like one example, for example. So first of all, we have to always we have to minimize the time that the equipment will fail. We have to try to design or choose the equipment that will be failing, in the minimum way, like minimum time, let's say minimum time per year or per month. Okay, so the equipment has to be designed to work continuously and to be reliable. So we need minimum maintenance, need minimum cost for maintenance. And okay, some example is, let's say for example for pump, compressor, those are the equipment that they continuously need maintenance, heat exchanger. So we need to, for example, for accessibility, we need to design such a lifting devices close to that equipment. We have to make sure that we have kind of like we have already planned and install some instruments, some devices that we can use to move that equipment. We can lift that equipment, put somewhere else, bring another new equipment, replace it, do the repair. So those are the things that need to be considered when we are designing the plant. Those are the details that has to be really considered carefully. Then okay, those are also some additional points about designing a process for maintainability, for maintenance. So we have to, as I said, for the pumps, for the compressors, we have to always install standby equipments. Let's say most of the time for the pumps we also install one parallel pump or one parallel compressor, so when the pump needs maintenance we switch to the other pump, to the parallel pump, so we do the maintenance, we fix it, and then we switch back to the main pump. So we need to design such a things in the process. And even the pipeline, we have to dedicate some pipeline that is used for purging, for maintenance, for this kind of work. Then as I said, we should design device, lifting device, moving devices to move the equipment, to lift them, like we have to locate them to be accessible. Those are the things that has to be we should have access to the pipeline easily, to the valves, to the equipment. Okay, those are some some additional information you can. So all the instruments, the control instruments, everything has to be accessible. We should be able to have access to them, to check them, to replace them. And also, okay, so we have to also consider the environmental impacts of maintenance. Let's say when you are cleaning something, when you are cleaning a compressor, a valve, or a pump that was operating with the toxic material, when you open that valve, when you open that equipment, there might be a spills of those toxic materials, or on the floor, or it might contaminate the working environmental. So we have to consider those things when we are going to do the maintenance. Then last slide of this unit is about okay, like we have also always for the maintenance requirement there are such curves or such figures that is usually prepared by the maintenance team, or even by the design team prior to the design and installation. Like it can be how easy or how difficult it is. Like we give different degrees of difficulty, or degree of we give the level of easiness or difficulty to different jobs that has to be done for maintenance. Let's say we need to know how easy is to have access to the equipment, if it is standardized equipment. What's the level of skill that we need to maintain that equipment? How often or after how long of usage it will fail? The material that is used is expensive or is cheap. Okay, selection of the equipment, online monitoring potential, lifting equipment that is needed, the environmental impact, some special tools to repair it, and the maintenance system that is needed. So those are the things that will be all considered for maintenance requirements. So that's all about this unit. Hopefully you enjoy it. So please go through this video and try to understand all the topics very well, and I will be always happy to answer your questions. Take care. and I will upload the video for unit 9 soon, okay, next week. Thank you.